Welcome to the second lecture of the week on statistics. Now, this will be a very basic overview of what statistics are, but it's important to know a little bit about the statistics that are in studies and researches and understand the basic concepts and what they mean so you can make better decisions. So our goals for this lecture is we're going to provide a basic review of the terms, both descriptive statistics and inferential statistics. Give you the knowledge to better understand scientific studies and make you more informed user of the numbers. There are no complex calculations, however, both on the quiz this week and on the first test, there will be basic calculations. I believe that you excuse me, you should be able to do them simply on a piece of scratch paper. No calculator would absolutely be needed, but most of your computers have calculators on them anyway. And I believe if I can figure out how to do it, I can put a calculator into the test and the quiz on ReggieNet to provide you that tool. I will look into that. So why statistics? Statistics help us understand risk better. They take raw data, and what they do is they translate it into useful information, and that information can be used to make decisions. If you, for an example, a very popular thing that has been going on for the last 10 years with forklifts, large companies that have lots of forklifts are attaching what is basically a black box to them. Their employees have to log in, and then that box can measure speed. Um, it has a GPS location on it. It can monitor idle time, engine running time, when the vehicle's actually in motion. It'll measure impacts. So if it hits something, it'll measure it. And some of the boxes have internal sensors that if you impact something hard enough, it'll shut it off. It's been my experience with these that they produce lots and lots of data. In fact, one of the projects I worked on this summer, I was receiving over 2,500 lines of data per day on 167 fork trucks. And it was my job to use this data to understand almost a behavioral analysis of the drivers. And statistics is how I analyze them by taking the like data and comparing it to each other and using it and breaking it down and coming out with something like even though we have 1,000 drivers, the data is only showing that only 450 people actually log in and use them. So that's why we use statistics in safety. And it's for those that go into safety, statistics and your risk and injury, your injury rates and your OSHA rates are all based on the types of injuries you have, when you have them, and how you have them. So the first, we'll start with descriptive statistics. So descriptive statistics in itself is what the data just says. It's you take your raw data set, you put it through processing software, or you do the numbers yourself, like we will, a very small data set, and the numbers that come out of it, which we'll get into on the next slide, um, are the description of that data. So the difference between descriptive and inferential is that descriptive talks about the data, inferential talks about what that data means onto something else, such as onto employee behavior. We'll talk about the central tendency concept and a little bit about variation and standard deviation. The central tendency of statistics, what we're going to cover are four different concepts: the mean, the median, the mode, and the range. The mean is the average, or we're going to add all the values together, divide by how many values we had, and get the average. Average and mean are pretty interchangeable, so if you happen to call the average the mean, or the mean the average, we're going to understand that in the class and not hold that against you. The median is the middle point. So if you have 29 values, your 15th value would be the middle point. That would be the median, no matter what it is. The mode is the most frequently appearing value, and the range is the numerical distance between the lower and the upper value. So the range is actually two things. You can have a range. I'll show you this example right here using this data set. The range here, and we'll talk about it a little bit more, is 79 to 150. So that is one way to describe the range. The range is also 71 units. So that's the difference between the lowest and the upper value. So using this example here, there are 30 test scores. As you can see, they're in no specific order. And what we want to do is calculate the statistics of this test. So the first thing we want to do is, when putting them in a spreadsheet, type them in however you want, but then you want to go ahead and put them in numerical order. The examples we will use on both the test and the quiz will not be a data set so large. We want to understand the basic concepts. So you would put this into a spreadsheet, or you'd write them all out and do the math by hand, and you would get that the mean is 124. So you added all 30 scores together, divided by 30, and got 124 as the average score for the test. When you put them in numerical order, top to bottom, the middle value would have been the 15th value from top to bottom was 127. Again, you put them in numerical order, you could identify the mode, which is 120, and that's the value that occurred the most. And then your range, as we just talked about, 79 to 150, the bottom value and the top value, and the range value is 171. So here is how that spreadsheet began. On the left side, just the scores, and then on the right side we put them in numerical order. And as you can see, the mean or the average, both columns, is the same. You can see on the right side where 120 shows up the most times, and the median value is the middle value. So variation. Also with statistics, you have what's called a standard deviation, and it's the common measure of the variability from the mean. All data has a standard deviation. It is the deviation itself, which we'll talk about, is the same for everything, but the value will be different based on the data. So in a normal distribution, you have this bell curve, and as you can see, 68% approximately value, all values will fall within one standard deviation of the mean. So here in the center is the mean, and then you have one sigma to the left and one sigma to the right. If you go two standard deviations or two sigmas to the left and to the right, you would get 95% of all the values. And then if you went three sigmas to the left and to the right, you would cover 99% of all values. If you, for a lot of you have heard of Lean Six Sigma, well, Six Sigma would be 99.999966% of all values. And for those that are going to go into business or actually into safety also, Lean Six Sigma is a process management to reduce errors. But we're going to be focused on just what 1 and 2 sigmas are. That's mainly how a lot of your studies will be out to the 95th percentile, or I'm sorry, 95%, or some will go out to 99%, and those are the p-values of studies, and that will be next week when we get into scientific studies. We'll cover those. So here's your test example again. The standard deviation for all of the test scores is 18.6. So that means approximately 68% of all the scores fall within 18.6 points above and below the mean. So our mean was 124, which is right here. That means that 68% of all of the scores fall within those 18 points, give or take this one standard deviation. Correlation and causation. Uh, correlation analysis provides a numerical rating of the relationship between variables. These ratings are quantified by a correlation coefficient and range from -1 to 1. So the three meanings. One means that if both variable, or if the correlation analysis provides a positive 1, that means that both the variables will increase in the same direction all the time. So one of the ways you can think about this, and it's a very crude idea, but as you apply heat to a pot, the temperature of water inside will raise. So the more heat that is applied, the higher temperature the water will be inside of the pot. And that would be a correlation coefficient of not necessarily 1, but close to a positive 1, because as the energy is put in increases, the heat will increase of the water. -1 means the variables move in the opposite direction. And the correlation coefficient gives an indication of really of how one variable moves in relation to the other. So going back to our boiling pot of water, if water is already boiling and I put it into a brand new pot and then continue to add heat, the temperature, once water reaches a boiling point, it doesn't get any hotter, it begins to evaporate. So if I add a little bit of heat, well, I should say if I'm adding constant heat and the water continues to boil, it's going to evaporate and the temperature is not necessarily going to rise anymore, but heat is going to increase. So a correlation coefficient in that sense might be closer to a -1 or more closer to 0, where it doesn't mean anything. Correlation does not mean causation. The two examples here, sale of ice cream and incident of heat strokes. So the idea with this is that in the summer it is hot, and because it's hot, there's an increased sale of ice cream to people. But also because it's hot, there is an increase of heat strokes or heat injuries. And so somebody could make the argument, it wouldn't be a very good one, but they could make the argument saying because it's hot and ice cream sales are high, we have high heat injuries, therefore ice cream is causing heat injuries. And that's not how it is. And as you get into your science classes, or if you've already taken them, you'll understand um, that those are not linked variables at all. So inferential statistics. Inferential statistics are drawing conclusions from the data. To do this, we have to use the scientific method. We develop our question, we construct a hypothesis, we test with our experiments. That's where we receive the data. We analyze those results. We either accept or reject our hypothesis. That's what the data is going to tell us. The data is either going to tell us, yes, what we hypothesized was correct, or it's going to say, no, your hypothesis is wrong. Using statistical methods to accept or reject the hypothesis. So there's three other concepts or definitions that we want to understand. One is the confidence interval, and that's the range of results that are within the confidence level. And these results are proven by the data and are not by chance. You have the p-value, and that's the probability that the results are due to chance and not to the hypothesis. And then you have a statistically significant number, and that's less than 5% probability chance that the results are just due to chance. Um, the example here is P equals 0.05. That's a 95% confidence interval. And what it's saying is that if you have a 0.05 p-value, that we are 95% confident that our data is statistically significant and it is not due to chance. The higher the p-value, the more chance there is that your results um, are due to chance or dumb luck. So the p-value, when you look at scientific studies, is very important because if somebody has a p-value of 0.5, where 50% chance that the results are due to luck or are skewed in some way, that doesn't become significant, and the values shouldn't be looked at and accepted that well. So health statistics are a little. They have a couple of their own little things, and being in safety or in health sciences or in general, you want to look at health statistics a little bit differently. They have unique measures in medical studies, advertisement, and news stories, and there'll be an example of this in the next couple slides here. One is the incident rate. So the incident rate is the number of the people with the disease divided by the number of people at risk. So if you want to think of this as a sample size versus a population size, the sample size of the population with the disease, let's say there's 1,000 people and 100 of them have the disease, you would divide that by the number of the population, which is 1,000, and you would get an incident rate. Lifetime odds versus the next 10 years is a time span. It greatly affects statistics. You have to look at, are they talking about how many people are going to contract a disease and die within the next 10 years, or if they contract a disease and die within their lifetime. Relative risk reduction, this is a number, and as you can see, that is the equation for it. You have your starting risk minus your modified risk, and then you divide it by your starting risk. And this is generally going to be a higher number, and we'll see this in the next slide or two. And then you have your absolute risk reduction, which is just your starting risk minus your modified risk. What you generally will see in news articles or studies is you will see the relative risk reduction because it's a much higher number and looks better in writing. And here is what I was talking about, your relative risk reduction of 42%. So this is a study with Zocor and heart disease. You've got two populations, one that we're given Zocor right here, and one that we're giving a placebo right here. And so you have a control group, that is the placebo, and then you have the group that is actually taking the medication. And then over the course of the study, Zocor led to mean reductions in total cholesterol, LDL cholesterol, and TG of 25%, 35%, and 10% respectively, and a mean increase of HDL cholesterol of 8%. Zocor significantly reduced the risk of mortality by 30%, and here's the p-value right here of 0.0003. There were 182 deaths in the Zocor group, so people did die, and I'm assuming of a heart-related disease, while on Zocor, versus 256 deaths in the placebo group. And here you go again. The CDHA, this is congestive heart disease, mortality was significantly reduced by 42%. So we take this study here and we put it into a spreadsheet, And so the top line here is placebo group. The bottom line is the Zocor group. And so you want to get your risk rate here. So you would take 189, you divide it by 2,223, and you would get 8.55%. And so you do the same thing, and you get 5%. So these are the risk incident rate in the groups. And then to get your relative risk, again, we have your starting risk minus the two risks divided by your starting, and you get the 41.5%. So that's how you get your risk reduction here. So we'll look at, again, your absolute risk reduction is just the risk, starting risk, and then you have so starting risk is the placebo group. They got no medication, so this is the group, this is the risk with no medication. And then your medication group, they got the Zocor. The study showed that they had a risk of 5%, and you subtract them, so your absolute risk reduction is 3.55%. So theoretically, what this is saying is that you have a 3.55% less likely chance of dying of heart disease by taking Zocor over a placebo. And so, and then what they did is they did in 5 years. So they must have done a 5-year study on this. And so we can see by the graph, these are they've graphed the risk percent, the risk of heart attack on the graph, with showing that the 3.5% reduction of risk by taking Zocor.